So in our discussion with Faraday's law, uh, we've always talked about this changing magnetic flux, but we'd like to have a way of relating something that's measurable to induced potential, and one of those things is current. So let's take a look at a quantity we're going to call mutual inductance, M, and it's going to be based on the mutual inductance, the effect on coil 2 based on coil 1. So subscripts are going to be very important here. And that is going to be equal to the number of turns in coil 2 times the flux that is between those two coils divided by the current in coil 1. So this is a relationship that we're going to manipulate. This is just some constant value that we're calculating based on the parameters that we have. And let's solve this for the flux. And that's just going to be equal to mutual inductance 2,1 times current 1 divided by the number of turns in coil 2. And if I'm going to take the derivative of my flux, and this is going to be a function of t, then that's just going to be equal to my mutual inductance 2,1 over N2 times the derivative of the current 1 dt. And now I can say that my induced potential due to coil 2 is equal to negative N2 d phi magnetic field, so my flux of the magnetic field changing in time. Substitute in for the flux, and that just leaves me with my mutual inductance in coil 2 due to coil 1 times the derivative of the current in the coil 1, how it's changing in time. And don't want to forget the minus sign here. Now, if I do the exact same expression for the other way, I get E1 is equal to negative M12 times the change in current in coil 2 with respect to time. So these relationships relate the induced potential to the current in the other coil, and usually M12 is equal to M21, and so that just leaves our formulas. E1 is equal to minus M times the current in the other coil with respect to time, and E2 is equal to negative M di1 dt. So this mutual inductance is very useful, and it's bidirectional between the two coils.